Okay, good morning, everyone. Welcome back to the GISS Sea Level Rise seminar. We're very glad to have Caitlin Locke with us today. She is a PhD student in the Polar Geophysics group in the Division of Marine and Polar Geophysics at the Lamont-Doherty Earth Observatory of Columbia University. And Caitlin's research focuses on understanding how the seafloor shape beneath Antarctic ice shelves influences ice flow. In addition to her current role as a PhD student, Caitlin has been a senior research staff assistant at LDEO since 2016, where she has conducted fieldwork in Antarctica and Greenland as part of the Rosetta Ice Project and NASA's Operation IceBridge. Prior to her work at Lamont, Caitlin was a senior research laboratory technician at the Gemological Institute of America and a data analyst and intern at LDEO and the Earth Institute, and also a professional ballet dancer in the Charleston Ballet Theater. Caitlin earned her MA in Earth and Environmental Science and BS in Earth Science from Columbia University. And today she will be speaking on the topic, Novel Record of Intermittent Grounding of the Venable Ice Shelf since 1935 from Operation IceBridge, Airborne-Gravity-Derived Bathymetry, and Landsat Imagery. So welcome, Caitlin.
Thank you, Patrick, and thank you everyone for being here. I'll go ahead and get started if that's okay. So as Patrick just said in his really nice introduction, my name is Caitlin Locke, and I'm a fourth-year PhD student at Lamont-Doherty Earth Observatory. And the title of my talk today is The Novel Record of Intermittent Grounding of the Venable Ice Shelf since 1935 from Operation IceBridge, Airborne-Gravity-Derived Bathymetry, and Landsat Imagery. And before I start, I just want to thank my co-authors, Kirsty Tinto, who's my PhD advisor, and then David Porter and Renata Constantino. Okay. So, and just to say, this research was recently published in GRL, so if after this talk you want to learn more, feel free to go and read it for more details. So to begin today, my outline of my talk will start with my motivation and background, and then we'll go into talking about the Venable Ice Shelf, and then I'll tell you about the survey area and the data we used for this study, and then our methods. Following that, our results and discussion, and then after that, some next steps for this research and some conclusions. Okay, so sea level rise will impact millions of people worldwide who live in coastal regions over the next few centuries. And here on this plot, you can see the blue line here is tide gauge data, and then the orange line here from 1992 onward is satellite data. And sea level rise from 1900 to 1990 was 1.2 millimeters per year. And then from 1990 to 2018, it increased to 1.6 millimeters per year. And then from 1993 to 2020, it's about 3.3 millimeters per year. And 40% of this sea level rise signature is due to thermal expansion trends, and 60% is due to mass increase from ice sheets and glacier melt. And here in our local area of New York City, this is a tide gauge data from the Battery in New York City. You can see the relative sea level trend is rising. And that sea level rise from 1856 to 2024 is currently 2.94 millimeters per year, which is equivalent to about a foot per 100 years. And sea level change has both global and regional drivers. The global drivers are these ice sheets and glaciers like the Greenland ice sheet and Antarctic ice sheet, in addition to steric expansion and groundwater. And there are also these regional drivers, such as the glacial isostatic adjustment, the gravitational pull of the ice sheets, subsidence, winds, currents, etc. For this, as I just mentioned, 60% of sea level rise is due to this mass increase from ice sheet and glacial melt. And here you can see that Greenland ice sheet has a 7-meter sea level equivalent. Glaciers have 0.5 meters of sea level equivalent, and the Antarctic ice sheet has 58 meters of sea level equivalent if it were to melt today. And Antarctica and Greenland contain the majority of Earth's fresh water and have this great potential to contribute to sea level change in the future. And back in our local area, this here are called sea level gradient fingerprint maps that show us where on the Greenland ice sheet and the Antarctic ice sheet sea level change will affect different port cities. And on the New York coast, sea level rise sensitivity is due to Antarctic and Greenland ice thickness change, particularly in the West Antarctic ice sheet here, and in Greenland in the northeastern portions of the Greenland ice sheet. Let's start this. Oh, it's going. Okay. So since this is a nice animation from 2002 onward to today, showing ice mass changes in both Antarctica and Greenland. And here the orange and red colors indicate ice mass loss, and the blue areas indicate ice mass gain, whereas the white areas indicate little to no change in ice mass. And as you can see in Antarctica, this is the West Antarctic ice sheet here, and it is losing a lot of mass and has been, and is continuing to lose a lot of ice mass. And this is where I will focus the rest of my talk today, in West Antarctica. So we'll let it go all the way to the end. Okay, so as I just said, accelerating mass loss from the Antarctic ice sheet is greatest in West Antarctica, and it's about 159 plus or minus 8 gigatons per year, particularly in the Amundsen Sea embayment and the Bellingshausen Sea Sector right here. And the Antarctic ice sheet gains mass through snow accumulation and then loses mass through submarine melting of ice shelves, and then also iceberg calving of ice shelves when the icebergs then melt. And around Antarctica, ice shelves form where that grounded ice flows into the ocean and begins to float. And these ice shelves play an important role in stabilizing the ice sheet through buttressing, where they restrain the flow from that grounded ice from the land to the ocean. And under these ice shelves, mass loss is concentrated where this warm circumpolar deep water has access to the subice shelf cavities and can facilitate this submarine melting and calving. And you can see in West Antarctica, there are certain ice shelves here that are warmer and have the circumpolar deep water under their ice shelves. And I, as Patrick mentioned, am interested in subice shelf bathymetry. And bathymetry, or water depth, you could call it, controls water circulation under these floating ice shelves and the interactions between the ice shelf and the seafloor. And I am particularly interested in the grounding line, this area here, where if there are no barriers of the bathymetry to that grounding line, this warm water can flow freely to that vulnerable area. However, if there are barriers such as like a bathymetric sill, then that groundwater cannot access the grounding line and is rerouted somewhere else. So here that brings me to our survey area, the Venable Ice Shelf, which is located in the Bellingshausen Sea Sector, right below the Antarctic Peninsula, right here. And you may be asking, like, why the Venable Ice Shelf? Other than that it was a target for the NASA Operation IceBridge project, it is also interesting scientifically, and here is why. So the Venable Ice Shelf, we knew, was behaving different from its Bellingshausen neighbors, showing that it was thinning extensively, but experiencing considerably less grounding line retreat than the rest of the region. And this was thought to be due to the suspected flux of circumpolar deep water to the grounding line along warm water ice shelf cavities, or troughs. However, before this study, the bed topography and how that ocean was circulating underneath the ice shelf was unknown. So I came along and decided that we should use airborne gravity data to model the bathymetry under the Venable Ice Shelf. And here I'm just going to tell you my key findings up front and then bring you through how we did this. So we did successfully create a new air-gravity-derived bathymetry model of the Venable Ice Shelf that mapped new pathways for warm ocean water to access this grounding line, in addition to identifying areas along that grounding line that are vulnerable to MCDW intrusions. And we also identified an intermittent grounding of the ice shelf on a newly identified pinning point that has been pinned since about 1935 on and off. And this was revealed by analyzing Landsat imagery. We used this combined analysis of Landsat imagery with our bathymetry model to provide evidence of mid-20th century Bellingshausen Sea Sector ice shelf thinning, which is a fun result. And also that the 1970s, there was a thickening episode that caused the Venable Ice Shelf to reground between 1970 and 1988. So now, how did we do all of this? So here, I'm going to bring you through our survey area and data. Okay, so we use data from the NASA Operation IceBridge mission, or OIB as I may call it from now on. And this was an airborne survey of the Earth's polar ice sheets, ice shelves, and sea ice designed to bridge the gap in observations between NASA's Ice Cloud and Land Elevation Satellite, or IceSat-1, that was decommissioned in 2009, and then the launch of IceSat-2, which was in 2018. So this was a 10-year-long project, and to date, it was the largest airborne survey of Antarctic and Arctic ice ever flown. And this study in particular used data from 6 flights flown in the Operation IceBridge mission between 2009 and 2017. And these were flown on here a P3, which are all these yellow lines, and that's me with the P3. And the DC-8 are all the black lines, and that's me underneath the tail of the DC-8 in Ushuaia, I believe. And these survey lines were 10 kilometers apart, and the aircraft flew at 460 meters above ground level and at a speed of like 265 knots or 135 meters per second, which gave us a resolution of about 5 kilometers for our gravity data, which I'll talk about. And on these flights, we were collecting ice thickness data, and these were, you can see here, from the multi-channel cohort radar depth sounder, which gave us ice shelf geometry data used to constrain our bathymetry models in these known areas. And then for the surface of the ice, we used the airborne topographic mapper laser altimeter data, which gave us ice surface elevation data. And then for offshore, we used multi-beam data that was compiled into the BedNap2 compilation from like a British Antarctic Survey cruise in 2007. And then for this unknown area beneath the ice shelf that we were interested in, we used our airborne inertially referenced gravimeter, or AirGrav, to collect our gravity data. And as you can see here, if you look here, gravity data is very interesting because high gravity anomaly values correspond to topographic highs where there is more mass detected under the aircraft, so like here and here. And then low gravity anomaly values correspond to topographic lows, like here and here, where there's less mass detected below the gravimeter as we're flying over it. And here we use this just under the ice shelf. And similarly, we were also collecting magnetic anomaly data from the cesium vapor magnetometer. And this magnetic anomaly data helped us identify geologic boundaries in our data that we could use to help constrain our model. And here again, I'm putting it right under the ice shelf to show you where we applied it in our models. And then again, in this unknown area to begin, we put in the BebNap2 bed topography data as our initial bed, and then use that to invert for a better fit. So our method. We were doing a gravity inversion for bathymetry. And we were doing this, and the main goal is to take something that looks flat or unknown to something that is a better bathymetry model. And we use this GMSys 2D software from Oasis Montage to build these models and invert for bathymetry along 8 survey lines, and these 2 here, using the Talwani two-dimensional 2D iterative forward modeling approach. And we put all of these data streams into our models. So we have the ice surface, the ice base, and the bed topography bed, and then also the gravity and magnetic data before we inverted. And along each of these survey lines, we put in these rock formation boundaries based on our magnetic data, gave them initial densities, and then we pinned our model. Right here, you can see we pinned it to a reference density column of ice, water, and rock, where it was defined by either radar or multi-beam bathymetry that was known. And then we inverted for the rest of the section for the bathymetry, and then also inverted for density simultaneously, so we could get a full picture of the survey along that line. And once we did that for all of our 8 profile models, we then gridded them together into a bathymetry model. So here we have our bathymetry model, and now I've put in Bed Machine 3, which is a bed topography map of Antarctica, and I differenced it with our new bathymetry model. So you can see that we have made it is very different in certain areas, and we've improved the model of the bathymetry under this ice shelf. And just to mention this here, those survey lines did actually go over the eastern portion of the Abbott ice shelf, which is down here, that had not been inverted for before. And here you can see this is the bed topography difference. So we have greatly improved the understanding of the ice shelf cavity by doing this bathymetry model. And what did we discover? Well, first, new deep pathways and troughs that can help this warm circumpolar deep water access the grounding line along these orange or yellow arrows. And also here, where there are circles along the grounding line, these are areas that we identified that are going to be vulnerable to modified circumpolar deep water currently, and the line within each circle indicates whether the slope was retrograde or prograde at that point, helping us further understand their future vulnerability. In addition to these deep pathways and the grounding line access, we also identified shallow regions in the ice shelf that were not previously known. And we did notice when we were looking at these shallow regions, I've put in this white box in these cyan places, these shallow regions, some of them corresponded to previously known pinning points from Matsuoka et al. And when we were looking at it and writing our discussion section, we noticed this new shallow area that we inverted for in our model in the western portion of the ice shelf that was not previously known or connected to a pinning point, which made us wonder, could this sub-ice shelf topographic high be a former pinning point? And if you're wondering, what is a pinning point? Pinning points are local sub-ice shelf bathymetric highs, like seen here, where the ice shelf is attached to it, or the ice shelf is attached to the ice base. And pinning points are important because they provide this buttressing to upstream ice flow, which reduces that ice discharge across the grounding line. And there is this previous study from last year from Miles and Bingham that used these satellite-derived surface expressions to measure ice shelf thickness change back to 1973 on the Venable Ice Shelf. And we were wondering if we could use this method and apply it here in a similar way. And what they did with this method is that they extended the record through the satellite era by proxy through measuring the change of the area of the pinning points. So in order to see if something similar could happen on this ice shelf with our newly identified bathymetric high, we collected all the Landsat data available without clouds from 1973 to 2024 in combination with our new bathymetry model. And we tried to understand if this was a past pinning point beneath the Venable Ice Shelf. And as I told you already, yes, we believe it is. And why? So looking at this Landsat imagery, we identified alternating crevassed and uncrevassed packets, like crevassed, uncrevassed, crevassed, in the Landsat imagery over the Venable Ice Shelf, and we interpret these to represent intermittent grounding of the ice shelf. And what we did is we used an ice velocity derived from crevasse change between a 1988 image and 2020 Landsat images to develop a grounding history. And from this change in crevasse over time, we had about a 656 meter per year velocity. So here is an image or a GIF I've stitched together of all the Landsat imagery over time. And you can see, if it restarts soon, that there will be crevasses propagating off this bathymetric high in 1973. And then they will slowly start marching towards the ice shelf front. So here they're forming, they unattach, and then they march towards the ice shelf front. And based on this, we propose a past pitting point beneath Venable Ice Shelf that has been intermittently grounded since 1935, before ungrounding most recently in 1988. So to bring you through that slowly, so we propose that this ice shelf was grounded between 1935 and 1958, as evidenced by these crevasses that would have formed here at this pitting point. And then it was ungrounded between 1958 and 1970, and then grounded again between 1970 and 1988, and then from 1988 on, it has been ungrounded and slowly moving downstream. So here, we now believe we can present a new method to extend the ice shelf thickness record beyond the satellite era. And this is modified from that Miles and Bingham figure here, where you can have a grounded ice shelf that has a large or new ice rumple with crevassing. And then you can also have a grounded ice shelf that has a smaller or no ice rumple with crevassing. And then you have an ungrounded ice shelf where there are smaller or no ice rumple with downstream crevasses still present because they have moved downstream. And this Miles and Bingham paper showed that thinning beneath this westernmost current ice rumple here at least 50 years ago. And then again, there was thinning along all of these current ice rumples since at least 35 years ago. And now, using our method, we believe we can show shelf thickness change since 1935, where the ice shelf was grounded on this ice rumple at least 89 years ago in 1935, and then it thinned between 1935 and 1958 until it ungrounded in 1958. And then it was grounded again on this ice rumple. And what's interesting during this time frame between 1970 and 1988, that the Miles and Bingham paper show thinning here, so there is a different signature happening, and we will discuss that later. And then this ice shelf ungrounded in 1988, and all of the ice rumples are shown to be thinning at that time. So here I've put this together into a graphic showing a timeline of this ice shelf thickness history. And I've also put down these Amundsen Sea ocean forcing reconstructions below it that are from central tropical Pacific sea surface temperatures. And what we discovered is that during this 1940s period when our ice shelf was grounded, it is synchronous with the thinning that was also in the Amundsen Sea embayment when Pine Island and Thwaites glaciers began to retreat in 1945. And this was following a major El Nino event between 1939 and 1942. And during those El Nino events, warming increases under ice shelves as more circumpolar deep water can access the continental shelf and go under these ice shelves if possible. We also showed that when our ice shelf regrounded in 1970, there was this thickening episode that caused this regrounding. And what is interesting, as I mentioned before, that the other Venable ice shelves saw either thinning or no detectable change during that time. So when we were writing this paper, we believed this suggested a more localized event due to ice stream dynamics of the Williams ice shelf, which is just below or upstream of this pitting point. So that concludes this paper, and so now I'm going to take you into the next steps and how we're using this method to investigate questions that arose during this study. So our next steps were investigating, in particular, this 1970s Antarctic ice shelf thickening episode using the same Landsat imagery and gravity-derived bathymetry analysis. And just to bring it back into why we're doing this, so in my paper I presented what I believe is a new method to extend the ice shelf thickness record beyond the satellite era using crevasses as a proxy. And we've shown that there is this 1940s Bellingshausen Sea Sector ice shelf thickening or thinning episode that was consistent with the timing of the Amundsen Sea embayment, thinning, and retreating in 1945. And what is interesting is that when our ice shelf is grounded and should be thinning to become ungrounded, in the Amundsen Sea embayment, there is a very large warm signature in the ocean in that time, which seems to make sense. However, during the 1970s, between 1970 and 1908, when there's evidence of a regrounding of the Venable Ice Shelf from a thickening episode, we initially attributed this to local dynamics, but now looking at this, you can see that it is regrounding here. But in the Amundsen Sea embayment, if we're thinking that they're all connected, there was a very large warming signature at that time, which made us wonder if this was more of a regional signal of thickening or if it was just local dynamics. And we believe now, after doing more investigation, that this is probably more of a regional signal. And why do we think that? Well, after publishing this paper, we decided to look at other ice shelves in the Bellingshausen Sea Sector and the Amundsen Sea embayment, and I decided to look at the George Ice Shelf, George VI Ice Shelf here, the Abbott Ice Shelf here, and the Dotson Ice Shelf here in the Amundsen Sea embayment. And we believe we see this 1970s thickening observed on all three of these ice shelves, which signifies a potentially more regional signature. So similarly to what we had done with the Venable Ice Shelf, we used Landsat imagery from all three ice shelves and modeled bathymetry products from the Venable Ice Shelf, or the Abbott Ice Shelf, which is our bathymetry model, the Dotson Ice Shelf from Jordan et al., and the George VI bathymetry model from Karasan et al. And here, this is the George VI Ice Shelf right here. And I'm looking at this tiny portion right here at the bottom edge. And in 1973, it's a bit hard to see, but there is a crevasse here in the satellite imagery. And on this image, this Landsat image, I've overlain the bathymetry contours. So you can sort of see there's this bathymetric high jutting out here. In particular, I want to look at this one, which is at 300 meters depth. And when we jump to 1986, suddenly we have more crevasses opening up during that time, which to me, based on our method, indicates a thickening of the ice shelf at that time, which would cause it to be stuck on this bathymetric high and crevasse. And then from 1989, it doesn't create more crevasses, just stuck there. And then after 89, it unpins seemingly, and then slowly starts to move away and then breaks up by 2014. And then now, if we jump down to the east, we can look at the eastern Abbott Ice Shelf, where here I've overlain this bathymetric contour, which is a bathymetric high here from our bathymetry model. And in 1973, you don't see anything, no crevassing around this. But by 1988, there are crevasses appearing around this bathymetric high. This one, I believe, is definitely from this one. This one is not totally clear whether it's from this tiny little bathymetric high right here or pitting point. And then from 1989 to 1997, there is another crevasse their crevasses move downstream, so I believe they've unpinned in that time, and then they slowly start to move towards the ice shelf front. And what's interesting, let's go back to this one is thickening and creating more crevasses around this pinning point right here. And then here on the Dotson Ice Shelf, between 1973 right here, this is a bathymetric contour I want you to focus on. There's one crevasse here. And then when you go to 1989, it's a bit hard to see, but there are two crevasses here that have formed during that time period, which to me indicates a thickening. And then from 1996, more crevasses are forming, continuing to crevasse to 2009 till 2019, and then to 2025, continuing to crevasse that entire time period. So we believe now that we have seen evidence of this thickening, and I would like to look into more ice shelves in the region just to further understand if it is a regional signal. And as I did with the Venable Ice Shelf, I did look into the grounding history based on the first available satellite imagery and back out what I believe are the timings and dates for those first crevasses seen at the ice shelf front. So here I've done the same with the Eastern Abbott Ice Shelf, the George Ice Shelf, and the Dotson. So here, this is the Eastern Abbott Ice Shelf. And if you believe me and what I've just said, that these crevasses potentially could become these crevasses here at the ice shelf front over time, based on the ice velocity over time, I calculated that between two different satellite images, there was about 100 meters per year of movement. And if that is true, then these crevasses would have formed in 1844 and 1814. And then if we go to the Dotson ice shelf, I again calculated an ice shelf velocity based on the difference in movement of crevasses between two satellite images, and that was about 269 meters per year. And based on that, I was able to assign ages to these crevasses, showing that there was a believed grounded period in 1830 and 1844, and then other episodes of grounding based on that time period, and I'll walk you through those. So specifically for this one, since it's a bit more complicated, I believe that, again, there was a grounding period between 1830 and 1844 here, and then it was ungrounded, and then grounded again between 1879 and 1883, ungrounded, and then grounded again between 1902 and 1937, ungrounded again, and then grounded from 1973 all the way to 2025. And what is interesting is that these areas that I've identified at the ice shelf front on both the George Ice Shelf and Dotson correspond to the Little Ice Age, which was between 1300 and 1850. And there is other evidence for Little Ice Age signatures in West Antarctica. So this is something I'm hoping to potentially see on other ice shelves and continue to explore. So that brings me to the end. So just like some conclusions. So I presented a new bathymetry model beneath the Venable Ice Shelf and also the Eastern Abbott Ice Shelf from an inversion of this Operation IceBridge gravity data. And we've modeled and mapped new pathways for more water to access the grounding line. We've identified a past pinning point beneath the Venable Ice Shelf in the western portion that has been intermittently grounded since about 1935. And we believe that this grounding history provides evidence of mid-20th century or 1940s Bellingshausen Sea Sector ice shelf thinning that is consistent with the timing of thinning with the neighboring Amundsen Sea embayment in 1945. We also believe we've shown evidence of regrounding of the Venable Ice Shelf between 1970 and 1988, and that we've seen this 1970s thickening also observed on the George VI Ice Shelf, Abbott Ice Shelf, and Dotson Ice Shelves, potentially meaning a more regional signature rather than local as we had initially determined. And we've also proposed that the Abbott and George Ice Shelf have been intermittently grounded on the paleo pinning points underneath their ice shelves since the early to mid 1800s during the Little Ice Age. And my next steps with this research are to continue analyzing other ice shelves in the Amundsen Sea embayment and the Bellingshausen Sea Sector for this 1970s ice shelf thickening episode in the 1970s. And if I can, I would like to explore the remaining ice shelves for similar ice shelf crevasses that correspond to these ice shelf bathymetric highs and see if I can determine other ice shelf thickness histories over time before the satellite era. And so with that, I just want to say thank you all for being here. And that just like funding for this work was provided by both NASA and NSF. And I can take questions now.
Thanks a lot. Do you have any questions?
I also meant to say I am in oceanography, so if anyone ever wants to come chat with me, you're welcome to come over to our humble abode.
I was wondering about if you can extend this to multiple ice shelves, like in an automated way or something.
Yes, I had someone ask me that at EGU too. I think that there is a possibility. Yeah, it's a little, yeah, and I think it is possible. I think I just haven't looked into it, and it is very nuanced because you are working with different bathymetry products and then trying to look at the crevasses in the same place. But it would definitely be a lot easier than me clicking through all of this Landsat imagery. So it would be nice to do that. So it's something potentially that we're going to look into. So it's not just me clicking through lots of imagery. Yeah. Thank you everyone for coming. It's very warm today.
Yeah, I guess another question is like, now that you have the longer record of these, of like how the climate was affecting ice shelves, like, is there something you can, what information does that add about? Could
Yeah.
it help like explain how it might change in the future?
Yeah. So I think that something I think that we think is really interesting is that if our grounding history, especially of the Venable Ice Shelf, revealed that we believe that the Bellingshausen Sea Sector and the Amundsen Sea Sector are experiencing similar regional effects in the 1940s after this El Nino event. So I think understanding that helps us think about the future and understanding if these systems are always connected and if there is a lag in time for when these warming events or thinning events occur, it'd be great to constrain those and understand those more to understand what our future could be like, especially since the Amundsen Sea embayment is warming and thinning very rapidly, and so is Bellingshausen. I think also it does show that like the Venable Ice Shelf is thinning extensively, but it has not been retreating like its neighbors or the other ice shelves in the Amundsen Sea embayment. And this is primarily seemingly due to these pinning points. And it just like shows how important they are and how knowing about past ones can really help us learn about past ice shelf history and maybe understand future pinning point buttressing and thinning off of them and what that can entail for ice shelf collapse. So yeah, I think there's lots of questions to investigate before I graduate. So. Yeah, thank you.
Thank you. Any other questions? Well, no, we can stop there. So.
I can stop sharing.
Okay.
Okay. Thanks everyone for coming.